Welcome to this explainer. Today we're diving straight into the fascinating world of shipbuilding. We're going to tackle a massive, honestly, mind-boggling engineering puzzle. How exactly do you find a microscopic, completely invisible flaw in a steel structure that's literally the size of a building?
Well, picture this. A worker is spraying a super simple soapy liquid along what looks, at least to the naked eye, like a perfectly flawless weld on a giant steel bulkhead. At first, nothing happens. But then, suddenly, a bubble slowly emerges at one spot. And then another. Boom! They've just found two completely invisible pinhole leaks. They fix both spots, respray the area, and when absolutely no bubbles form, the weld passes. This whole process brilliantly illustrates a much larger challenge in shipbuilding. Like, what's the alternative when you simply cannot flood a giant structural compartment with thousands of tons of water to test its integrity? Hydrostatic testing, filling it with water, is the standard, sure, but it's just not always possible.
Which brings us to Section 1, the soap bubble solution, also known as air pressure testing.
The procedure here is wonderfully straightforward. First up, you completely seal the space. Second, you pressurize it just enough to drive air through any potential microscopic leaks, but definitely not enough to cause structural damage. Third, you apply that soapy solution we talked about to all the exterior weld seams. And finally, you just watch for bubbles. It's really that simple. But it's truly fascinating here? It's the remarkably low gauge pressure used for this test. We're talking typically just 0.15 to 0.20 bar. To put that number into perspective, we are only raising the pressure a tiny 15 to 20 kilopascals above normal everyday atmospheric conditions. It's a very, very slight increase. But crucially, it's more than enough to force air through a tiny defect and blow a visible bubble. So let's move into Section 2, the danger of compressed air, and exactly why that pressure stays so low. You might be wondering why they don't just crank the pressure up. Well, it all comes down to how different elements behave. Air is a gas, right? And it's highly compressible. When you pump it into a sealed tank, it acts exactly like a tightly coiled spring. Water, on the other hand, is an incompressible liquid. If water leaks, the pressure drops instantly, and almost zero energy is stored. This means a tank full of compressed air stores an explosive amount of energy. In fact, it stores a staggering 200 times more energy than the exact same volume of water sitting at the exact same pressure. Just think about that. 200 times. So imagine if a large structural defect actually gave way during a high-pressure air test. That spring-like stored energy would be released explosively, literally tearing the steel plates apart with catastrophic force. That is exactly why high-pressure air testing of structural compartments is considered extremely dangerous and is strictly prohibited by classification society rules. Safety dictates we absolutely have to keep that pressure low. Moving on to Section 3, ideal for bubble tests, and the practical applications of this method. So where do we actually use this low-pressure air technique? Well, it's the absolute go-to solution for spaces on the ship that just can't be conveniently flooded. Think about complex void spaces, narrow cofferdams, and pipe tunnel bulkheads. It's also perfectly suited for intertank bulkheads. Say one side is already full of water from an adjacent tank test. You just pressurize the empty side and look for those telltale bubbles. And beyond just being the only real option for some of these tricky spaces, it's an incredibly practical and fast solution overall. It completely bypasses the massive, time-consuming logistical nightmare of pumping thousands of tons of water in and out of the ship just to check a few weld seams. And finally, Section 4, ready for launch and the final structural steps. By now, through rigorous visual checks, X-rays, ultrasound, water testing, and of course, these clever little soap bubbles, every single inch of the vessel has been scrutinized. With every invisible pinhole found and fixed, and every tank proven to be completely watertight, the ship has officially conquered its structural testing phase. The steel is perfectly sound. Which leaves us with one final, kind of breathtaking thought. After all this meticulous, microscopic testing on dry land, how will thousands of tons of steel actually behave when it's finally subjected to the raw, dynamic power of the ocean? I hope this explainer leaves you eager to find out exactly how these massive vessels handle taking their very first swim.